It's a pleasure to be here today, and what I'm talking about is interdisciplinary learning, and we've been focusing on that all week, interdisciplinary, because our goal is to integrate in the state of Ohio, where I'm from, in the United States, is inquiry-based learning for our students at Wright State University. And we're looking at curriculum to meet the 21st century. In the 21st century right now, the state is requiring us to follow certain standards. And how do we meet problem solving? So our earlier speaker was excellent talking about engineering and how these different disciplinaries are coming together. Because in the modules that I'll be demonstrating today, I will be talking about how we're trying to put science, technology, engineering, and math together to create interdisciplinary experiences for our students so they can meet the state standards. And we'll talk about what those standards are as well. So the pedagogical strategies that we're trying to go through is, what is the goal of science education? Well, like I said, we want it to be interdisciplinary. We want them to be problem-based solvers, critical thinking skills. These are vital issues. And the thing that they're pushing upon us is the next generation of science standards. And so I'm a researcher in electrochemistry, but I also teach chemical education. So my whole goal is I'm meeting those high school teachers or those K through 12 teachers. I also teach early childhood and middle childhood science education. How do we make sure they hit the next generation of science standards? Because they just recently came out. And the National Science Teaching Association. These are vital. And for the 21st century, if you get the Science magazine every month from the American Association for Advancement of Science, it talks about these issues and career building skills for our students to be problem-based learners and to meet the needs in the field. So for instance, we might have science education majors, but then they decide to become researchers. But I also tell my teaching students that you might also want to be teaching and then in the summer get a research job. So you have to have all the skills needed to meet the needs of the world so you can be the best person in the field possible to get the job. So this is what the framework in the 21st century talks about. And it talks about interdisciplinary meetings, science, technology, engineering, and math. The math and engineering is vital to make sure students learn. And within these life and career skills, the biggest thing that Brendan Gill has been talking about at his university, they're expecting him to do communication. Communication skills is something that we expect our students to do to get a job. But do we really teach communication skills? Grandin has talked about this too. And that's a problem. So how do we address that issue to meet those students' needs to be successful in the real world? And that's what the life and career skills want us to do. So we have to work with that. Learning and innovation skills. What are the 4 C's in the innovation and learning skills for the 21st century that they're requiring us to do? It's a kind of like a tier, basically. If you talk about the framework of the 21st century and those 4 C's we've been talking about, obviously the first one, communication. We've been talking about that. Critical thinking skills. Joanne has emphasized critical thinking skills all day yesterday, how vital that is for our students to problem-based learning and critical thinking skills for the real world. And communication with the collaboration, because as you know, working in groups, they learn. Like Joanne said, sometimes you've got that one kid that wants to sit back and let everybody do the work. But it's how you monitor the situation and how you assess the situation that all students must be engaged. So the clue is, how do you assess your students to make sure they're all engaged as they're working collaboratively? And innovation. We've talked about innovation, creativity. That's the other C, creativity. So we want them to be creative and as they're being critical thinkers, so that they're not just copying off someone's page or looking something up in the literature and not thinking on their own how to innovate their own ideas. So within my curriculum, I'm going to show you today some actual results of some research modules that students in electrochemical aspects, talking about chemistry and engineering, how they come together. And obviously without the math, they can't survive. And I'm going to show you some of those aspects with water quality, because I think water quality is an interest to all of us, because we don't want to die from drinking bad water. So and within communication, you can see when they address that in a report how important that is to all students. And then the ICT skills. Obviously, in interdisciplinary, as we're talking about, we're looking for, when I talk about ICT skills for the 21st century, what does that mean? It means information, communication, but also technology. So in the information, communication, and technology, as your engineering professor has emphasized to you today, is that it's very important for them to learn how to utilize software and to know how to solve problems as they're solving them, how to graph them, or use different types of software to analyze the situation and what is the reasoning that they come to this decision. Is it a better sensor or a worse sensor? Because today, within the electrochemistry, we're going to talk about sensors for water quality. So in the state and throughout the standards I'm talking to you about, the next generation of science standards. There's core subjects. The core subjects in K through 12, we're trying to meet our students here in the United States. Obviously, we wanted to take English, language arts, civics, geography, the basic things in English. But then the big thing we have is science and math, and that's where they struggle so much. And we don't have the United States, we don't have the top scientists anymore. So how do we engage our students to want to be scientists and work in science, technology, engineering, and math? So that is the goal within the core subjects, talking about interdisciplinary. And when we talk about those tiers coming off those core subjects, the biggest things they want them to do is come up with global awareness. So as we talk about global awareness in science, why, as even as in civics come together too, civic literacy and global awareness. So as you become a voter, a decision maker, how do you decide if that sensor is the best thing in the environment? They might say, oh, it's going to kill everybody in the world if they use that sensor. So we're trying to make them think about global awareness and literacy with civic literacy, but also environmental literacy and health literacy. As he talked to you this morning, that health is very vital, looking at how you're going to segment and pinpoint where you want to actually hit that tumor. Those problem-based skills are vital for our students. And so we try to integrate all those. And the last one here would really much hit what Grandin's talking about as well, business. So in the EL, that's more of the business entrepreneurial literacy. How do you become an entrepreneur and create a business such as Joanne has done in her field as well? So Joanne's not only a professor, she's what you would call the critical thinking skill example of what we want our students to be doing. She runs her own business and she's a professor. She can do various things in the world. So that's our goal for our students, to have all these particular things come together. How do we meet those standards? And so I'm going to show you some curriculum that I have developed that I think has helped meet our students a little bit, but it's not perfect, of course. And so that's why I'm taking a sabbatical next year, and I'll be working on case studies and how to develop further problem-based solving. And in science, we know, as we say, there's only one answer. But we want them to also think beyond that one answer. We want them to think about how do you problem-base a problem that you don't really, there's multiple ways to solve the problem. So that's another thing we want to look at. And so I want to create case studies next year with the University of Central Florida to see if I can come up how to do instrumentation with that, with this technology I'm talking about. So typically, I'm just going to go through the basic theory of traditional learning. Typically in chemistry or any science, what had happened in the past in the United States is that people would just go off and give the facts, and the teacher would, and then the student would just receive the knowledge. And unfortunately, like Joanne said, there's still some universities that don't want to look at problem-based learning, so they go back to the stand-up and lecture and the kids sleep. So we don't want the cookbook method. We really don't. We want them to think on their own. So to meet these standards, we're using inquiry-based learning. In inquiry-based learning, we're hitting the National Science Education Standards. Remember, it's something that the students do and not something that is done for them. So they're making their own decisions. They're following the scientific method. We know that's vital for the K through 12 standards. They have evidence to support their direction of what they're saying and what they plan on doing within the next steps of the experimentational process. And also, I'm acting as a facilitator. I'm not standing up and just today, I know this is kind of boring because I'm standing up, and I was going to give you a demo, but I didn't actually able to get on the plane with chemicals, as Joanne said. There's problems with flying, that's for sure. But I could have given you a demo and asked you what you thought about the polymers and why the water might have left and what happened. And so there's different ways you can generate being the facilitator without being the lecturer, because we know if the student actually sees it and does it, they really get it. And then obviously you want them to become independent thinkers, and that's what our goals are when we talk about global awareness and civic literacy and environmental literacy and hitting the health literacy and the entrepreneurial literacy, those points which the 21st century is really wanting us to do as professors. So the 5 E's. In education, the 5 E's that we try to hit in any type of lesson plan that a student puts together or portfolio, in the 5 E's we're looking at engage, explore, explain, extend, and evaluate. So as they're going through, and they've already done experimentational processes with me, at the end of the whole thing in the science education courses, they have to create a portfolio and make sure they implement the 5 E's within that, because that's a vital part. There's different levels of inquiry. Obviously, there's open inquiry, guided inquiry, structured inquiry, and limited inquiry. I consider mine to be more of the guided inquiry, but there's points where you can go in between. as Grandin was even saying about case studies the other day, it was very informative about, if you look at his book and you start reading it, you'll see that it talks about sometimes you can't just go through a basic case study, you have to go through a walkthrough case study before your students can really go into the next steps. And so the same thing here with inquiry, some of the things overlap and you have to work maybe structured a little bit with guided at times. It's not all just one type of inquiry as well, but I call it more guided, but there's other types within that, within your lesson plan. So this just goes into what J.W. Lehman said about disciplinary and why it's important. And the biggest things I just put in yellow, because obviously you can read the slide yourself, was provide experiences and build new knowledge. So our goal is to provide experiences and build new knowledge. But remember, in an interdisciplinary field, it helps them. Why? Because it's diverse settings. Diversity helps them. You want to create different diverse settings, different types of ways to analyze the problem. And it makes them become more powerful, is what it's basically saying to you, as making them feel more confident. Because we know when we have students go and present data at conferences, sometimes they're not as confident, and then somebody comes up and asks them a question, and then they draw back and they feel like they can't answer it. So working to that, they can feel more confident on their own to problem solve and think about what that person's asking as well. And so I like what also Mark Van Doren says. He says the art of teaching is the art of assisting discovery. And I think that Phyllis should really represent this to her colleagues, because obviously it's discovery, it's problem-based, and discovery in the classroom, and ICT skills, information, communication, and technology skills, as well as what he talks about. So obviously we've talked about the main things of what inquiry are, and the goal of them is communicating scientific arguments. So anytime somebody says they're doing inquiry-based learning, what they're doing is they're asking questions to the students. So in other words, you're not just giving the student the answer in the lecture. They're planning and conducting investigations. The students are doing that. The professor's not doing that. You might have the equipment set up for them, and then therefore they have to figure out what equipment do they need to utilize. They have to gather the data. You're not the one in there just demoing it, like in a lecture hall, and here's the graph, and this is what you get. Because if they gather the data, and then they have to think about it logically and graph it themselves and use software and technology, and then conduct scientific arguments why this happened or why that happened. And then they can utilize literature. That's not bad, because they can back up why they think something happened or why they think something didn't happen. Because the other day I talked about anti-corrosion for nails and roofing. So anti-corrosion is really important here in the United States for nails. And so what they did was, in the students in this particular K through 12 setting, it was actually a middle school setting, they had to come up with the argument, why did their solution synthesis work better than in others groups, and argument why theirs was better. And it came into the concept of coordination chemistry. So it built upon knowledge. So I like what Breton El Chalet says, and I've used this slide before in the past because I really think it talks about us as children. And I think we forget, because as we get older and we're teaching, sometimes we forget what we were like as children and how much fun it was to be a child because you had no bills to pay. But also it was fun because you were raising questions and trying to answer questions about the world in which we live. And also it would involve experimentation, creativity, and problem solving and playing as a child to understand the world. So you didn't quite understand it, and we still don't understand it, even as a grown-up at times, obviously. So we're always trying to understand it. But as a child, it's a lot of fun, isn't it, to creative and problem solve. You get this new game, and you want to figure out how to put it together. You want to figure out why it's working, why isn't it working, or if you break something, how can you put it together? Children really enjoy doing that. We're grown-ups, we get mad now. Why isn't that working? So this is just a revisitation of what's the difference between traditional and inquiry classrooms. And I know Joan uses inquiry classrooms, so this is nothing new to Joan, right, Joan? So, but at least it gives you an aspect of, how we look at it and how it's different and why we think inquiry works better. Later today, as I go on into the talk, I'm going to talk about our Heike and how we assess the pre-test and the post-test to see the content gains and the students' knowledge in these modules as well. So the class structure that typically works well, as Grandin told you, if you have too large of a classroom, you really can't engage with your students. You want to have a small classroom size so you can work better with them, and you can also facilitate each group accordingly. Like this would be a good set of classroom because we have each table set up that you guys could be working along with your equipment. Obviously, integrated lab, you can have a discussion at times because you know all times groups need sometimes a discussion about why something's happening and make them go back and rethink about it, but kind of leading them along is what I do. I don't actually give them the answer because that's a bad process. And then I like the part at the end, I require them to do authentic forms of assessment so I can see what's going on in terms of assessment with them. So, characteristics of the 21st century. This is kind of what I want to say about the research exploration is the outcome is not known in advance. So in this particular program, I'm going to show you that they had to figure out how to create a sensor to detect lead and cadmium. And these are people that are going to be high school teachers, so a little more higher tiered. And they might go on to get PhDs, these particular students that I'm demoing with their data for today. So it's higher tiered than what I showed you the other day. In middle school, I was showing you more of a project. And the middle school curriculum was coming up with a synthesis to coat nails for anti-corrosion. In this case, we're looking for how can we detect heavy metals in water, contaminants. And the three heavy metals that I'm going to focus on today is lead, cadmium, and arsenic, which is a big concern, right? So as you go along, what is the natural integration with the courses? So you want to integrate chemistry, engineering, and math. And what a lot of people do in chemistry, I've noticed, even the lectures, some of the courses we offer, the students come to me and even tell me now that they've had me is that their physical chemistry, they don't see how it relates to anything. And then so I go back and I get really upset because they've just sat through a lecture and they really don't understand why they're doing it. But if you think about the Schrodinger equation, which has got tons of, obviously it's calculus, you can't live without the Schrodinger equation. And if you go deeper into the Schrodinger equation, you can understand more about the particle, the electron, and what's going on. And then you can go deeper and get into Raman and IR activity. So there's a lot of use of math, and that's where I get worried when my students tell me they just really didn't get why they were sitting there. So I can understand that, and so I try to integrate my courses so it's not like that. They can critical think and they can see where they're headed and why they're taking something or doing something. So critical thinking and problem solving show the relevance of modern problems, and that's what the water quality purpose was really, and collaboration and communication among learning communities. And I think students really work well when they're collaborating because they really get to discuss it more. So if you actually have a lecture hall and they all leave and they don't talk anymore, to me that's really a waste of time because this way they get to learn each other's name, become friends, and they work throughout. Sometimes even what I found after my 18 years being at Wright State University, sometimes my students will go and try for the same jobs and they communicate throughout their careers that way. They become friends and they become mentors and they can say, well, this is working or that's not working. So this communication is vital even to continue on with your career. So benefits of interdisciplinary learning, obviously they're more comfortable, I have found, in the electroanalytical chemistry modules. They learn to use new equipment. So when I talk about technology, when we talk about software, I'm also talking about different types of technology like Raman, spectroscopy, FTIR for transform infrared spectroscopy. CV is cyclic photometry today, and square wave anodic stripping photometry. And the biggest thing is I've had students actually take an electrochemistry course from somebody else, not me, and they couldn't still tell me the difference after they come to my lab about CV and SW ASV. And that was disturbing to me because, so if you had water samples, why can't you run all your water samples by cyclic photometry versus square wave anodic stripping photometry? And the students didn't understand concentration's an issue. Because if you're in the real world and you have a heavy metal and it's a really, really low concentration, you have to use square wave anodic stripping photometry to detect it. So how do you utilize this technology too within these interdisciplinaries? And again, pre and post assessment is very important to see if your students have gained content knowledge. So again, the metals I said I'm going to focus on is lead and cadmium and arsenic, how to utilize a cyclic photomegram versus square wave anodic stripping photometry, other types of instrumentation which I'll show you today. And I won't show you the XRF today, the X-ray fluorescence, but I'll mainly focus on today really the CV and the square wave anodic stripping photometry and the SEM to see the differences in the surface once they create the sensor. How do they know that the sensor is really working or what's on the electrode surface of the sensor? Because you can't see it with your eye. So how can you prove that to me? And they have to figure out what instrumentation they need to really utilize. So this is a 3-electrode compartment cell. And when we talked about real-world skills today, he was talking about when you have cancer and you're looking at how do you pinpoint to hit that cancer cell. Same concept with electrodes because actually electrodes are very public health utilized. You can use glucose sensors if you have, obviously if you have sugar, so that's electrochemistry. So they learn to utilize these electrodes, and we actually have an experiment too, which I didn't show you today, how they can look at glucose sensors and how to create glucose sensors. And today we're just looking at water quality, but you can see where electrochemistry is vital in the health field. and also neurotransmitters in the brain if you're looking at a patient that has Parkinson's or no Parkinson's. So this is very important. So this is a 3 electrode compartment cell. And the biggest thing is you can either purchase a working electrode or you can make your own working electrode. And so I'm going to show you 2 scenarios. One is they have to make their own electrode. They have to figure out how to make their own electrode. And I'm utilizing this group who did the best electrode making, obviously, versus I couldn't show you the group that did the bad electrode because then you wouldn't think my class was cool. But obviously, like you said, no answer is always the right answer, right? It takes many, many trials to make something work. And so I agree with what you said the other day sometimes, but there are bad results. If you've seen some groups, you would cry. But that's experimentation, right? So you have some groups that get it and some groups that don't. So anyway, they had to look at synthesis and the different types of sol gels. And what I do is they obviously have to use literature. And reading in our field, I feel at Wright State University, students don't like to read. I don't know if anybody else comes across that problem. But that's where I think literature is important, searching, because they get to learn to read the literature and make their own decisions and then try the experiment and say, well, that's not what you really wanted to do, so you wanted to try this. Well, why did you try that? Well, because the literature said this, but I wanted to try this. So it had to be novel synthesis. It couldn't be exactly what the literature said, and then they had to optimize it. So these were the particular sol gels they looked at, was titanium and zirconium, which are cheap electrodes to make, is why. That was picked because we're on a budget too at Wright State University, with a carbon paste electrode building to coat them with this titanium and zirconium surface. But they had to look at how do they want to synthesize it, because I told them they couldn't follow the synthesis that had been done in the past in the literature. So they had to look at what types of parameters do they want to optimize to make that the best sensor. And then for arsenic, what the choice was, I gave various electrodes instead of coating the electrodes in this particular group. They had to look at different types like silver, gold, platinum, carbon that you just purchase, and they don't make them themselves. But can they detect arsenic was the question. So the biggest thing is when you think about even integrating the sciences, one of the things in electrochemistry we look at is pH. You know that's a biological thing as well. So you can see where biology and chemistry come together as well. Not only pH, they had to look at temperature, which I'm going to focus today on temperature more for the synthesis, and the different types of analysis, CV and square wave analytic stripping photometry. And I'll show you what the differences of those are as we go along. So this is basically the synthesis, just telling you what they tried: a graph pipe powder, 1.5 milliliters of methyl trimethyl methoxysilane, 0.3 milliliters of 1 molar H2SO4, 0.5 milliliters of isopropanol. And the part that they had to change, what this group particularly did, which did better than the other groups, was looking at the literature and deciding crystallization was a factor. So the parameter that they changed was looking at the surfactant, tween 20 versus tween 80. So in an engineering field, that's important. They're looking at how do they optimize that parameter and the problem-based solving there to do that. So here's the ratios we're looking at within that they did, and they looked at temperature duration. So I'll just briefly show you when we talk about technology why it's important, because I know you're not excited about the sensor as much as I am, but you're looking more at the process skills, right, Joan? So if you look at the process skills, here we have current milliamps versus heating condition. They learned to graph. They learned technological skills. And that's really important as an undergrad. And they had to figure out what was the optimized parameter as they chose. So they chose 290 at 10 minutes, 290 at 20. So you see what, 375 versus 375 at 20 minutes. And what you see is the 375 at 10 minutes had the most optimum detection according to this is bicyclic photometry. They've seen that they could detect lead because this is a higher reading, right? So they're learning how to utilize their graphs. So at 375 in 10 minutes, they got better detection for lead. The question is, will that work also for cadmium? So as they tried it, they looked at the same temperatures, the same timing, heating conditions, and if you look here, again, 375 at 10 minutes, cadmium's detected. It's not as strong of a signal for cadmium, but you have a signal for cadmium, don't you? So as you go through, here's this talking about the crystalline processes, and that's what I'm talking about. The tween 20 and the tween 80 was what they were looking at, how they optimized choosing the right surfactant in the process. And so there's ratios to look at what ratio worked best: titanium, zirconium, or zirconium only for the sol gel synthesis. And the biggest thing they find is, obviously, it's a titanium-zirconium ratio that happens for the detection of lead. which is really good for the students to learn about, again, graphing. Can everybody see that? So I went a little more detailed than our engineering professor because I told him too much, didn't I? And the cadmium, same thing. More detail in terms of the synthesis, but again, you can look, the 2-to-1 ratio, right guys, is giving you on the tween 80 the best signal. So that's why the tween 80 is chosen. So what we're looking at is tween 20 versus tween 80, and they graph it. So I think it's nice to see a visual graph by them anyway to show them that they are doing that. So this was the final optimization, and this is the final parameters this particular group did. So what does that tell you? So now what do they need to do? Well, can they really detect it? So let's see what it looks like. With cyclic photometry, what you have is you have a graph of current versus potential, and you have an oxidation reduction peak, and if you look here, you have the different scan rates showing you how it varies in the detection of lead, don't you? So what they do is they can plot and figure out what type is a rate, once you do further into electrochemistry, what is the rate of the reaction is the purpose of this, doing different scan rates for lead and cadmium. But can they detect low detection limits? So I'm going to show you how square wave analytic stripping photometry, they had to play around with the parameters. It is software compatible. So they had to look at, was this the best deposition time? So they had to do many trials. I'm only showing you the optimum results. Many trials to figure out what was the best way to detect with square wave analytic stripping photometry for these electrodes built. So here's square wave analytic stripping photometry, and what's so neat is you can see that you can get 1 part per billion, 5 part per billion, and 10 part per billion. And obviously it makes sense that you can see the different types of, obviously the higher the concentration, the deeper the peak, right? Same thing here. You have 40 to 160 part per billion, and what you see here is obviously this is the 40 and this is the 160. What also is really challenging for these students is making solutions. It's making those concentrations in the solutions. It sounds easy, but it's serial dilution sometimes, and then what is serial addition for this case? So because they had to keep spiking it. But how do you know what that concentration is? Because it's math involved. It's math intensive. So that's another point. It looks easier than what it is as I go through the talking of it, but it is intensive how they have to think about it. So they have plotted current versus concentration, a linear calibration. And obviously what's interesting is the concentrations down here, it's not perfectly linear to the next, but again, this is undergrad research, so we don't yell at them. And this is cadmium. So you can see cadmium, the same concept. You see your peaks. You only get 1 peak for cadmium. The reason is, when you look at cyclic photometry, I didn't get to tell you the differences there too. You get an oxidation reduction peak. When you're doing square wave analytic stripping photometry, and you think about the engineering process of that, what you're doing is you're going to strip off. First you have to strip it off, and then you reapply the metal. So in other words, you deposit the metal for so many minutes, and then you strip it off, and that's when you get the detection, and you only get an oxidation peak for square wave analytic stripping photometry. So they do get the different techniques, and they're getting lower concentrations, as you can see, down to up the 60 parts per billion, which is right here, the orange one, and 120, obviously the more concentrated. And a linear calibration curve. So that's very important, again, software compatibility. And then the question is, can you detect the two simultaneously? So then they had to figure out how to make up the solution that had cadmium and lead. Now, this can go further into an analysis. You can give them a real-world water sample and see if they can detect lead and cadmium. And that's the next step of this particular thing is once they make their solutions and they see it works, does it really work for a real-world water sample? This is a water sample where they've spiked it with lead and cadmium to explain to you why that data looks so beautiful. And so the first peak is, what do you think the first peak is since we've been looking at the data all this time? First peak is lead, and the second peak is cadmium. Everyone agree? Because we've seen the lead was more, so it detected lead better. Everyone agree? And again, just looking at different concentrations, 200 parts per billion versus 60 parts per billion. And this is the SEM. So now we've taken it a step further. We've looked at detecting them. They know they've made an electrode that can detect lead and cadmium. Now the question is, are you really sure you have something? Do you really sure that soil gel is on the surface? Are you sure there's crystallization? How do you really know? And so then they have to do SEM analysis. And that's, again, a more high-tiered thing, scanning electron microscopy. So can we see where technology is vital? And when we're implementing real-world analysis into it, but we're also making them learn new instrumentation, which is quite challenging at times. So it's a lot of work for the student. And this is just an example of arsenic water. And basically, in the arsenic water, they had various concentrations. This is an example of 60 ppb detected. And so another module created was, can you detect arsenic in water? And when you detect arsenic in water, what type of electrode do you want to utilize? And so if you actually took a platinum electrode, you would see no peak. Like, there would be no arsenic peak. Like, this is an arsenic peak right here. If you come down, this is the arsenic peak. But if you would have done a platinum electrode, you would get no detection. This is actually a gold electrode. And so I wish I would have showed you some of the results so you could see why the student had to realize that gold was the metal of choice opposed to platinum or carbon for arsenic, because of the factor that when you read the literature, they talk about gold plating. So with that, when you give them those different electrodes, they have to explain why gold is better. You see why it's a little more problem-based? And then there is an example of the arsenic in silver. So can we see the silver is not detecting as well? This is on gold back here, and this is on silver. So the peak is not nearly as nice, is it? And then this shows you that you can do various concentrations like we were talking about with arsenic, doing parts per billion. So now in the real world, you may not have parts per billion. You might have parts per trillion, right? Or you might have parts per million, which is a high concentration that can kill you. So you want to know what are the levels in your water and can you detect them. So the thing they learned too is cyclic photometry can detect parts per million maybe. Really 10 to the minus 5 molarity reality-wise. And square wave anodic stripping photometry can detect really low concentrations. So what does the tell us really? And then they do a linear calibration again, and it's not beautiful data for the arsenic because it's like a 0.98, and we know we want it close to 1. But you can see that these are undergrads, and they are doing their own work, which is great to see, and they're learning the new software, how to graph items and make analysis of them. So the desired learning outcomes to really talk about what is our purpose today. Our purpose because we're all not chemists, our purpose is to create interdisciplinary content that can relate to problem solving, but relate to skills where our students can get a job anywhere. So not only in education, but also now they can walk into industry and they can do water quality testing. They can understand problem-based water quality, or they can even go further and maybe they're interested not just in water quality, maybe they're interested in scanning electron microscopy and how that's utilized in the geology and chemistry field, because we have a company in Ohio called the Bowser-Morner Company. And the Bowser-Morner Company has been in business for over 150 years. And I have chemists I work with, and until I taught them about the Bowser-Morner Company, they knew nothing about it. They do geology and chemistry. That's how they build the roads and the bridges. So how does the geology and the chemistry come together to build the roads and infrastructures and the bridges that we have? So, and tensile strength. So I really enjoy the engineering and the chemistry part and the geology because they all do come together. You can't live without one or the other, really. And the math is vital, too. So your goal as a professor is obviously to come up with interdisciplinary that students relate appropriately and deploy to real-world problems so they have an interest. Because if you teach a lesson on tensile strength and you don't relate it anyway to the bridge collapsing, they really don't care. They don't really care, at least my students don't. So I try to make it real world so they do care, so they see why they're doing it. Because I think in physical chemistry even, that is the problem. That is the challenge we face, is they don't see why they're doing it and then they get very frustrated. So if you create your curriculum interdisciplinary and you build it among your colleagues might be talking about geology. How can you put geology and chemistry together? So if you're teaching a business class and it's finance, how can you create, as Brandon was talking about, your taxes? We know our taxes are coming due here in the United States. How can you create a lesson plan that relates to a problem that we all have to do? So skills and outcomes, perform technical procedures. As you can see, they're performing technical procedures, which I think is really important to do that and think critically. Effective outcomes. Obviously, we want them to have ethical behavior. We don't want them to copy off each other's work. If the results aren't working, I agree with the young man the other day talking about sometimes results don't work, and that's a great thing sometimes. Because it makes a student step back and ask why it doesn't work, and they can go to the next step and try something else, and then figure out a little further. And so every lab, and we don't always grade on the results, because if you do that, what happens is, then they do cheat. I don't know if you remember the ARG when they used to like test aspirin, you had to come up with a certain percentage of aspirin. You remember those, Jays, Dr. Reed? And if you didn't come up with that percentage, you know, one kid was cheating and trying to like scrape up some white powder and put it in the aspirin. Yeah. And then what would happen is when you take the melting point, the professor knew that like you took some other powder somewhere else, white powder, and mixed it with your product, so you would act like it was aspirin, so you would get a higher grade. That's what they did in my era. I don't know. So, and I'm sure they do the same thing. I don't teach organic anymore, but I remember the days. So, and I would always just face it. You know, I didn't have the high percentage of aspirin, but some kids just took the bad road because they want to get in med school no matter what. So that's a bad way. So we want to teach ethical skills. We also want to teach them that it's okay to be wrong. It's okay that you didn't work it out. We have extra hours in lab. We can work as well, and you can get better skills. And I actually keep the lab open at all times I'm on campus. And I even stay extra late. I run a class like I might go in at 8 a.m. and I'll stay until 10 p.m. to make sure all students have the accessibility to the lab, because that's the whole goal, is to give them the hands-on experiences and the knowledge and skills they need for the world. And I like Dr. Wells' concept here about accreditation and student learning outcomes. This is a great resource if you ever have a chance on that. And assessment is very important. I believe in assessment, pre and posting. And there's some examples in the Journal of Chem Ed, which I've utilized, and in analytical chemistry. And also, some of this is also from Purdue University, because they're very much into inquiry-based learning, just down the road from us in Indianapolis. So, guiding inquiry, you want your students to work in groups, that's okay, and you want to provide guidance and summarize important learning goals. So, and these just give you some more references. So, like if you look at this reference right here, learning in a laboratory environment and chemical education towards research-based practices, that is actually from Purdue University, and it really talks about cognitive skills being built as well. And Joanne yesterday, Dr. Reed told you, Dr. Joanne Reed told you that when you're looking at Edgar Dale's triangle or pyramid, what you're seeing is that cognitive skills can be built when you're working more in the inquiry-based mode. And that's very vital, and they have found success in that. So when you do pre and post assessments, what do you typically find? What do you typically find that your students are doing? Why would you say inquiry works better? So for instance, when Phyllis is competing with her dean about inquiry-based versus our critical thinking skills versus lecture, if you actually take R.R. Hakey, he's a physicist, in the Journal of Physics, he talks about assessment. And you take a pre-test of your students, and then you take a post-test. And if you do this every time, you'll see that there's a gain in content knowledge. And you take someone else's lecture hall, a pre-test versus a post-test, when you do a lecture, you'll find that the post-test, the pre and the post, the gain stays very low. You have 0.3 to 0.7 to 0.3 medium gain. But when you do inquiry-based learning, typically it's been noted it's going to be 0.7 or higher. And that's taking the pre and the post. So for instance, a normalized gain on the heavy metal detection in water was 0.73. So we're seeing a gain. It's almost not quite a high gain, but the big thing is that we are seeing a bigger gain than we've seen when we were lecturing, because the students did not get the skills or touch the instrumentation needed to really give them the learning processes of what they need to be doing for the real world and global awareness, why water quality is important. And these are just pictures of my students, because I'm so proud of them. Here she is doing synthesis under the hood, running the instrumentation. In this case, she's looking at a cyclic photomegram. It's just a potentiostat. You can also do square wave analytic stripping photometry on this instrument. This is Corey showing you the electrode. Unfortunately, you can't see the electrode. It's just a little electrode's all it is. And it's very hard to see in that picture, but it's a capillary tube. So showing you that there it is, that you can build it very easily. And different instrumentation, so Raman spec, things that they've encountered, X-ray fluorescence. So I just want to thank everyone for your attention today, and I hope that everyone enjoyed the talk, and I hope it just innovates you to go back and think about, are my students learning, and what can I do to help my students, because they are the future of this world, and all of you are the future of this world. And I thank everyone from all over the world for coming here, because it's so nice. This is what I like about this interdisciplinary. We all are from different areas, and we can all work together to help each other. So if anybody has any questions or needs any assistance or any instrumentation, what we do, we'd be happy to help you. Thank you very much for your time today.